So in the previous video, we saw BFS algorithm and we explored all the paths or nodes in the graph. And I gave you a task to find the goal node R, and then your task was to return that path. And your path should look something like this. This should be the output. So if you have watched the previous video on BFS algorithm and you have watched how we did a dry run and explained the whole code, then this was a very easy task to do. So let's see how we solve this. So this is the BFS algorithm which we have discussed in the previous video. And if you have not watched the previous video, please do watch that because I have explained the whole algorithm and code in detail. So now what I will do is I will add one more parameter to our function as goal. And when we are pushing the neighbors of the front node into the queue, what we will do is we will check that neighbor is equal to our goal node or not. If the neighbor is equal to the goal node, we will return the path immediately. And if it's not equal to the goal node, then we will keep exploring the goal node. So I will write an if statement here that if the neighbor is equal to our goal, then we will return the path immediately. And if the goal node is not available in the search space at that time, we will just return none. But here we have one edge case that if our goal node is the source node itself, then it will not be detected in this for loop, in this if statement, and it will search and at last it will return none. So at the start what we will do is we will write a if statement that if s is equal to goal, then what we will do is sorry then what we will do is we will directly return a list with s in it, and that's it. If we run this code, sorry, I will write r as our goal node here. In the main function I will pass the argument in the BFS function, and if I run this, so this was the expected output. So if I compare this to what we discussed earlier, so this was our output which we discussed, and if I compare this to what we got, these both are same. So this is how you find a goal node using BFS. But BFS algorithm is known to find the shortest path to the goal node. But here we are not finding the shortest path because we are traversing through all the nodes in breadth area. So how to find the shortest path using BFS algorithm? So we will see that with the example of a binary tree. So if I take the example of this binary tree and give you the goal node as O and ask you to find the goal node, so you know how to do it. We have already discussed the whole process and whole code regarding this algorithm. So what you will simply do is you will use a BFS algorithm, and what you will do is you will create a path, and in that path you will append your source node first. So in this case the source node will be A. Then what you will do is you will go to the next level and check if goal node is there or not. So this will be our next level, and you will check that in this level is your goal node available or not. So it is not available in this level, so you will append the neighbors of the source node in the path. Now after you have explored the whole level, you will go to the next level again and find if the goal node is available in that level or not. In this case it is not available. You will simply put all the explored nodes in the path. So in this case we will append P, Q, R and S. R and S. So now you will again go to the next level, which will be the last level of the tree. And at the last level, we will start pushing the elements one by one. So from the last level, first we will push L, then we will push M in the path, then we will push N, and at last we will push O and check if we have got the goal node or not. So in this case our goal node was O and we have got the goal node, and we will at last return the path. But is there any optimal way to do it? So now in order to find the shortest path, what we will do is we will perform the same BFS algorithm. That is, we will traverse level by level, exploring all the nodes, and once we reach our goal node, we will return. But the different thing we will do is we will keep a check on the parents. So what I will do is when we traverse the first level, that is the source node, and then we move to the next level, that is C and D. So what I will do is I will keep a check on the parents of C and D. That is somewhere in the dictionary or anywhere. I will store the parents of C and D. So in this case, the parent of C and D will be A. Then again, we will move to the next level. In this case, the next level is P, Q, R, and S. And again, I will store the parents of those nodes. Then again, I will move to the next level and I will again store the parents of those nodes. So this will benefit us in order to find the shortest path. So how it will do, let's see. So when we will find the goal node, which is O in this case, so in the dictionary we will be having all the parents and all their children. So what I will just ask O, who is your parent? So O will tell me that S is my parent. Okay, then I will ask S, that who is your parent? S will tell me that D is my parent. Then I will ask D, that who is your parent? D will tell me A is my parent. And in this case we will find the shortest path that will reach the goal node. So shortest path will be A, D, S, and O. So process will be, I will be asking O that who is your parent. O will tell me S. I will be asking S who is your parent. S will tell me D. I will ask D who is your parent. D will tell me A. And at last I will just reverse them. So we will get the shortest path as A, D, S, and O. So this is how we find the shortest path. Now let's see how we will do this in graph. And after we have seen how we will find the shortest path in the graph, we will see how to write that in code. And I will also try run the code at the end. So the things will get very clear in your mind. So now let's see how to find the shortest path in the graph. So what we will do is we will apply the same BFS algorithm. That is, we will traverse level by level, exploring all the nodes. But what we will do is we will keep a check of each of parent of each node in the dictionary. So what we will do is we will first traverse the source node, that is level 0. So we know that we will append the source node in the path. At the same time, what we will do is we will append the parent of source node in the path. So in this case, the parent of source node will be none because A does not have any parent. So parent of A will be none. Okay. So now we will move to the next level as we do in the BFS algorithm. We will move to level 1 and explore all the nodes. So at level 1, the node will be S. So we will write the parent of S, which will be A. So the parent of S will be A. So now we have explored the level 1. Now we will move to next level and explore the nodes, which will be P and Q, and write the parents of P and Q in the dictionary. So the parents of both P and Q will be S. So let's write this. The parent of Q will be S. And at the same time, the parent of P will also be S. So we will write the parent of P. So now as we have explored the level 2, we will move to level 3, which will be R and T. So now let's write the parent of node R, which will be Q. And important point to note that the parent of R will be Q and not P. We will see that how it is when we dry run the whole code. So for now, just remember that parent of R will be Q and not P. So parent of R will be Q. Then we will move to node T, and the parent of node T will again be Q. So we will be writing that in our dictionary. Okay, so now let's move to our last level, which is B, and write the parent of B, which will be T. So the parent of B is T. Okay, at start I forgot to mention the goal node. So let's assume that our goal was B. Okay, so now as soon as we reach the goal B, the program, as we know, the program will terminate and we will return the path. But this time, we will not return the path. We will go into the dictionary. and we will go into the dictionary and we will ask our goal node that who is your parent. So we will go to B and ask that who is your parent. B will tell that T is my parent. Okay, so we will write B, then B will tell us who is the parent of B. So the parent of B will be T. Okay, so now we will go to T. So we will move to T. So now ask T that who is your parent. T will tell that Q is my parent. Okay, we will append that in our list. So now go to T and ask that who is your parent. So now we will go to Q. So we will directly move here. And we will ask Q that who is your parent. Q will tell that S is my parent. So we will append S in the path. So now again we will move to S and ask that who is your parent to S. S will tell that A is my parent. So we will append A in the list, and then we will move to A and ask A who is your parent, and A will tell I have no parent. So as soon as we reach the node which have no parent, we will end the program. But before terminating the program, what we will do is we will reverse this path. So now our path will look like A, then A from A to S, from S to Q, from Q we will move to T, and from T finally we will reach our goal node B, and at last we will return this path. So this is how we will find the shortest path. So now let's quickly go to the code and implement this algorithm of shortest path, and at last we will be dry running this code so it will get very clear in your mind. So I have taken the same BFS code which we discussed earlier, and in this what we did was once we find the goal node, we return the path immediately. But for the shortest path, what we will do is we will not return the path immediately. Instead, what we will do is at first we will create a parent dictionary in which we will be storing the parent of each node in the graph. So first we will store the parent of our source node, which will be none. And in this dictionary, the key represents the node which you are storing, and its value represents the parent of that node. And we know that we will be following the same process as BFS. So we will run a while loop till we have at least one element in the queue, and we will be popping out the front element of the queue and then pushing its neighbors in the queue. And what we will do is we will not append in the path. Don't worry if you're not understanding, I will dry run this at the end and it will get very clear in your mind. So we don't need path right now. We will be needing that, but not right now. Okay, so now what we do is in BFS, we pop the front element of the queue and push its neighbors in the queue. And at the same time, we add it in the visited list and in the path. But this time we don't need path. So while exploring the neighbors of the popped element, what we will do is we will append the parent of that neighbor in the dictionary. So what I will do is I will write parent of neighbor. So you can tell that parent of neighbor will be front, which is the popped element of the queue. So once we do this, what we will do is we will check that if our neighbor is equal to goal, and if is equal to goal, we will not return the path immediately. What we will do is instead we will assign a variable current to goal, and we will create an empty list path. So don't worry if you are not understanding. I will dry run this at the end and it will get very clear in your mind. And we will write a loop till our current is not none. So why do I do this? Because we know that once we reach a node whose parent is none, we return the path, reverse path, and we terminate the program. So what I will do is I will append the current in the path, and I will change the value of current to its parent. And once we do this, we will return the reverse path. Sorry, we will return the reverse path. And if the goal node is not available in the search space, we will return none, or else we can also return like no goal state available. So now if I run this program, I will also change our goal node because we know that we have taken the goal node as B. So I will quickly change it. And now if I run the program, you can see we have got our shortest path. So if I compare to what we discussed earlier, so this was the path which we discussed earlier, and if I paste our output here, so you can see this both are same. So what we did was very correct, and let's try run this program to get things very clear. So now let's try run this and get things very clear. So at first what we do is we append our source node in the queue and also in the visited list. So let's do it. We will take the source node which is A, and we will push it in the queue, and at the same time we will also add it in the visited list. And next what we do is we create a parent dictionary in which we will be storing the node and its parent. So node will be stored as key and parent will be its value. So at first we will store S with its parent as none. So in the dictionary, the parent of A will be none. Okay. So now next we will do the same as we do in the BFS. We will run a while loop till our queue is not empty, and we will pop the first element of the queue. So we will pop A out of the queue, and we know we will append the neighbors of A in the queue as well as in the visited list. So neighbor of A will be S, and we will push it in the queue. At the same time, we will add it in the visited list. So now we have explored all the neighbors of A. So far we have completed these two tasks. We have appended the neighbors in the queue and also in the visited list. So in the parent dictionary, what we will do is we will write the parent of neighbor as front. So we know that our neighbor is S and front is nothing but the pop element of the queue, which is A for now. So the parent of S will become A, and we will write this in the dictionary. So the parent of S will be A. So this if statement is over. Now we will move to another if statement. So here we will check that is our neighbor equal to goal. So our goal is node B. So our neighbor is S. So is it equal? No. So this if statement will not run, and this for loop will terminate because we have only one neighbor of A. And we will again move to the while loop, and we will check that whether the length of queue is greater than 0. So in this case, it is greater than 0. So this loop will sustain, and again we will pop the front element. So we will pop S, and we know that we append the neighbors of S in the queue. So we will append the first neighbor, which will be Q. So we will append Q. For this will be for the first iteration. So we will take Q and push it in the queue. At the same time, we know we will also add it in the visited list. So now again, we completed these two tasks. Now we will perform this. So parent of Q will be front element, which is popped element. So here the front element was S, which was also the popped element of the queue. So we will write in the dictionary the parent of Q as S. Okay. So now this if statement is completed, we will move to next statement. So we will check if our neighbor is equal to goal. So in this case, our neighbor is Q. So is it equal to goal? No, because goal is B. So this if statement will not run, and again we will move to our next iteration. So we will move to our next neighbor, which is P in this case. So we will take P and append it in the queue. At the same time, we will push it in the visited list. Now the parent of P will be the front, which is again the popped element, which is S. So in the dictionary, we will write the parent of P as S again. So this if statement will terminate and we will move to our next if. So we will check if neighbor is equal to goal. So P is not equal to B. So this if statement will not run and this loop will terminate as we have explored all the neighbors of node S. And again, we will move to the while loop and check if the length of Q is greater than 0. So yes, the length of Q is greater than 0. And again, we will pop the front element and push its neighbors in the queue. So the neighbors of Q will be first neighbor of Q will be R. So let's push R in the queue and at the same time in the visited list. So now first iteration our neighbor was R, and we have completed these two tasks, pushing in the queue and also pushing it in the visited list. So the parent of the parent of R. So here the parent of R will become the front element, which is nothing but the popped element Q. So the parent of R will be Q. So we will move to our next if statement and check whether our neighbor is equal to goal. So R is not equal to B. So this if statement will not run. And again, we will run the for loop for next iteration. For next iteration, our neighbor will be T. So let's push our neighbor in the queue and also in the visited list. So again, we completed our two tasks of pushing in the queue and in the visited list. And now we will append the parent of our neighbor. So our neighbor is T. So the parent of T will become the front element, which is nothing but the popped element Q. So in the dictionary, I will write parent of T as Q. Okay, once we do this, we will move to our next if and check if neighbor is equal to goal. So T is not equal to B. So the if statement will not run and our for loop will terminate because we have explored all the neighbors. And now we will again move to the while loop and check if our queue is empty or not. No, our queue is not empty. We will again pop the front element, push its neighbor in the queue. So the neighbors of P are S and R, which are already present in the visited list. So nothing will happen. Now again, we will pop R out of Q and again check for its neighbors. So for Q, we will not append it in the queue because it is already present in the visited list. And also for P, we will not append it as it is already present in the visited list. So now for R, we have explored all the neighbors Q, P. So now the for loop will terminate and then we will move to our while loop and check if the length of Q is greater than 0 or not. So yes, the length of Q is greater than 0. So we know that we will pop the front element out. So we will pop T and then search for its neighbors. So the neighbors of T will be B. So Q will also be the neighbor of T, but as we know that it is already present in the visited list, so we will not be taking it. So we will take B this time as it is not present in the visited list. Push it in the queue. At the same time, add it in the visited list. So now we have completed these two tasks. As we know, we have pushed our neighbor in the queue and also in the visited list. So now what we will be doing is that we will be appending the parent of B as front in the dictionary. So the parent of B, as we know, it will be the popped element, which is the front element of the B, that is T. So we will write the parent of B as T. So we will be adding that in the dictionary. And once we do it, and now here comes the main part. So what we will do is we have completed all these three. Now we will move to our next if and check if neighbor is equal to goal. So now in this case our neighbor is B and our goal is also B. So now this if statement will run. So now in if statement what we will do is we will take a variable current and assign goal to it. So what we will do is we will take a variable current. So this will be our current and which will be equal to B as B is our goal. Okay. So now what we will do is we will create an empty list as path and we will run a loop till our current is not none. Let's see what happens. So now in the while loop, we will append current in the path. So let's do it. For first iteration, our current is B, which is not none. So while loop will sustain. So we will add current in the path. So let's do this. So our current is B. So we will add node B in the path. So we will add this in the in the path, sorry. And now we will change the value of current to the parent of current. So we know our current is right now B and we will change current to the parent of current. So our current B will change to the parent of B. So we know we will search in the dictionary the parent of B, which is T in this case. So our current will be changed to T. Again, we will go to while loop. Our current is still not none, it is T. So while loop will sustain and we will append the current in the path. So we will append our node T in the path. So you can see what we are just doing is we are just backtracking the parents and reaching the source node. And once we reach the source node, we will just reverse the path. So this is the basic thinking behind this. So again, we have appended in the path and we will change the our current to the parent. So the value of current is T and the parent of T is Q. So now current will become Q. Again, the while loop will sustain because current is not none. Again, we will add the current in the path. So we will add Q in the path. As you can see that we are just backtracking the parent and reaching the source node. So it is very easy. And again, we will change our current to its parent. So the parent of Q will be S. So again, we will write S here. The while loop will still sustain because current is not none. Again, we will be appending our current in the path. So let's do it. Our current is S. So where is S? Okay. We will append S in the path. Again, the current will be changed to its parent. The parent of S will be A. So you can see how we are reaching the source node. So the current will be A. Again, we will append it in our path. Sorry. Okay. We will take A and push it in the path. Again, we will change the current to its parent. So now what will happen is our current was A. So once we search in the dictionary the parent of A, it will be none. So now the value of current will be none. And as we know that once the value of current is none, the while loop will terminate. And now we will return the reverse path. Why? Because we were backtracking and we reached the source node, but we want a path from source node to goal node. So we will reverse it. So now the path will just become, so now this will be our path, reverse path, which will be the final path of the shortest path in the BFS algorithm. So this is how we reach a goal node in shortest path using BFS algorithm. And this method of backtracking parent and reaching the source node and then reversing the path is we will be also using it in the greedy best first search algorithm and also in the A-star algorithm. So I just wanted to show you how to do it so we can use it in the further videos. So that's how we do it. So now in the next video we will be seeing depth first search algorithm and we will be doing the same task. We will also find the path which will lead us to a goal, and we will see that all in the next video. So for now, that's it, and thank you.